Lennard-Jones potential. The potential energy of two atoms in a diatomic molecule is approximated by potential energy as a function of R is A divided by R to the power 12 minus B divided by R to the power 6, where R is the spacing between atoms and A and B are positive constants. Part A. Find the force F as a function of R on one atom. Draw two graphs, one of potential energy versus R and one of force versus R. Part B. Find the equilibrium distance between the two atoms. Is this equilibrium stable? Part C. Suppose the distance between the two atoms is equal to the equilibrium distance found in Part B. What minimum energy must be added to the molecule to dissociate it, that is, to separate the two atoms to an infinite distance apart? This is called the dissociation energy of the molecule. Part D. For the molecule carbon monoxide, the equilibrium distance between the carbon and oxygen atoms is 1.13 10 to minus 10 meters or angstroms, 1.13 angstroms, and the dissociation energy is 1.54 times 10 to minus 18 joules per mole per molecule. Find the values of the constants A and B. So let's start with part A. We have a potential energy function U as a function of R given by constant A divided by R to the 12th minus constant B divided by R to 6. So the force that corresponds to this potential energy function will be equal to minus derivative of the potential energy function with respect to its only variable R, the distance between the two atoms. So if I take a derivative, I obtain R to the minus 12 derivative gives me A times minus 12 R to the minus 13. So this will be A minus 12 divided by R to the 13 minus, then I have R to minus 6, that gives me minus 6 R to minus 7. So minus B minus 6 divided by R to the 7. So the answer is, because the minus minus here will become plus, 6B divided by R to 7 minus 12A divided by R to 13. Okay, so this is our force as a function of distance between the two atoms. Now, in order to plot these functions, I'm going to analyze them a little bit. So what happens to the potential energy function as R goes to 0? So if I look at the limit as R goes to 0, A divided by R to the 12 minus B divided by R to 6, this will be the limit as R goes to 0, 1 over R to the 6th power, A divided by R to 6 minus B. So you can see that 1 over R to 6, R goes to 0 will give us infinity multiplied by infinity minus B, which is infinite. So the potential energy goes to infinity as R goes to 0. And what happens when R goes to infinity, infinite separation? A divided by R to 12 minus B divided by R to 6. Well, as R goes to infinity, both terms go to 0. 0 minus 0, we obtain 0. So the potential energy in this limit should asymptotically approach 0. If I look at the derivative of potential energy with respect to r, du dr, and set it equal to 0 to find the extremum point, I can see that this is when the force is equal to 0. So we have 6b divided by r to 7 minus 12a divided by r to 13 equals to 0. So 1 over r to 7 parentheses, we have 6b minus 12a divided by r to 6 equals to 0. So this has the following solution. R can be infinite, or we find an equilibrium distance r0, which is found by looking at the root of this, and it's going to be 6b equals 12a over r to 6. So r to 6 will become 12a over 6b. So 12a divided by 6b to the power 1 over 2, or 2a divided by b to the power 1 over, it was 1 over 6. So this is 1 over 6. This is 1 over 6. And the potential energy at 0 is infinite. The potential energy at r0, the equilibrium point, will be equal to a divided by 2a over b, 12 to the power 12 over 6, minus b divided by 2a over b, 6 over 6. Okay, so we continue evaluating the potential energy function at the equilibrium point. So we find that u at r0 must be equal to a divided by so 12 over 6 gives us 2, so it's going to be 4a squared over b squared. 4a squared divided by b squared in the denominator, and minus 2a over b, 6 over 6 is 1. B goes upstairs, it becomes b squared. B squared divided by 2a, and this gives us ab squared divided by 4a squared minus b squared over 2a. The one of the a's will disappear here, and this is going to become in 4a parentheses, so it's going to be b squared minus 2b squared divided by 4a. So we will find that this is minus b squared over 4a, which is negative because we have a and b positive. It's a minimum. A minimum in the potential energy function is found by setting the force equal to 0. So based on these observations, if I plot the potential energy function as r goes to 0, it goes to infinity. At r equals r0, we have a negative value of the potential energy function. As r goes to infinity, it goes to 0. So this is the potential energy function, and its derivative minus du dr. We can analyze the behavior of the slope here. When r is less than r0 in this regime, you can see that the derivative du dr is negative. du dr is negative, force is minus du dr, so the force is going to be positive. So between 0 and r0, the force has to be positive, which means they have a repulsive interaction. There is a repulsive interaction between the atoms. They are pushing each other away. At r equals r0, we obtain du dr equals to 0. That's when I have equilibrium point. That's when the force is equal to 0. Then I have r greater than r0. du dr is positive. As you can see here, the derivative becomes positive. Therefore, the force minus du dr goes negative. And as r goes to infinity, du dr goes to 0. So the force at infinite distance has to be 0. So we see that there is a minimum for this function as well. And in this range, the force is negative, so we have attractive region. Okay, so let's move on to part B. Part B is asking us to find the equilibrium distance, and is this equilibrium stable? All right, so equilibrium distance between the atoms is obtained when the force between them is 0, and that is what we have found here, this value of r0, which we have found in part A. It was 2, let's see here, it is this value, 2a over b, 2a over b to the power 1 over 6. So this is the equilibrium distance between the atoms. So if I look at the second derivative of the potential energy function, d square u dr square, so I take another derivative of the potential energy function, so derivative of this, I'm going to obtain from this term, there's going to be a minus 7, r to the minus 7, so this will give us minus 7 times 6b divided by r to the 8. So we obtain minus 7 times 6b divided by r to the 8. And from this term, I will obtain minus 13 times minus 12 divided by r to 14. So this will give me plus minus 13 minus 12 a divided by r to the 14. So if I calculate this, this becomes 156a divided by r to 14 minus 42b divided by r to 8. So if I evaluate the second derivative of potential energy, d square u dr square, at the equilibrium point, r equals r0, this will become 156a divided by 2a over b to the power 1 over 6, so we have to the power 14 over 6, minus 42b divided by 2a over b to the power now 8 over 6. So this gives us 156 a b to the power 7 over 3 divided by 2 to the 14 a to the 14 minus 42b b to the power 4 over 3 divided by 2 to the 8 a to the 8. So this is going to be roughly, if I calculate 156 divided by 2 to the 14, 0.01 b to the 7 over 3 divided by a to 13, because there was one a on top, it becomes a to 13 at the bottom, and 42 divided by 2 to the 8 gives me 0.16 b to the power 7 over 3 divided by a to 8. Why 7 over 3? Because we're 4 over 3 plus 1. So you can see that this number here is smaller than this number. We have a to 13, so this is a lot smaller than this one. So therefore the second derivative is negative, and second derivative being negative, we find that we have a stable equilibrium. This can also be seen by looking at the sign change at r equals r0. So you can see that we have a negative slope here and a positive slope here. So there's a sign change in the slope, and the second derivative basically reflects the sign change and giving us a stable equilibrium. So part C asks us suppose the distance between the two atoms is equal to the equilibrium distance found in part B, to find the minimum energy that must be added to the molecule to dissociate it. All right. So in part C, I have the potential energy equal to minus b squared over 4a at the equilibrium point. That's what I have found here by evaluating the potential energy at the equilibrium point. Now, the dissociation energy is when I separate them to infinite distance from the equilibrium point. So how much energy do I need to add? At an infinite distance, the potential energy is 0. At the equilibrium point, it's minus b squared over 4a, so plus b squared over 4a. So b squared over 4a is the energy I have to add to separate them to infinite distance. Therefore, the dissociation energy is b squared over 4a. Now part D is an application of this for the molecule carbon monoxide. We have equilibrium distance between carbon monoxide molecules 1.13 times 10 to minus 10 meters, and the dissociation energy is 1.54 times 10 to the minus 18 joules per molecule. And we have the equilibrium distance between molecules 2a over b to the power 1 over 6, and the dissociation energy is b squared over 4a. So when we plug in the numbers here, the equilibrium distance 2a over b to the power 1 over 6 should be 1.13 times 10 to minus 10 meters. So we find that 2a over b, 2a to b ratio is 1.13 times 10 to minus 10 to the power 6. So we find that 2a is equal to 1.13 times 10 to minus 10 to the power 6b, or 4a is equal to 2b times 1.13 times 10 to the minus 10 to the power 6. Now, the dissociation energy is 1.54 10 to minus 8 joules per 18 joules per molecule, and this is equal to b square over 4a, so it is b square divided by 4a, and 4a is given here, so I substitute that. B square divided by 2b, 1.13 10 to minus 10 to the power 6, so one of the b's will disappear, and we find b to be 1.54 times 10 to the minus 18 multiplied by 2 multiplied by 1.13 times 10 to minus 10 to the power 6. If you calculate this, this is 6.41 times 10 to the minus 78 joules meters to the 6th power. Why is the unit joules meters to the 6th power? Go back to the potential energy function. This term has to be in joules. These two are energy terms, so it has to be divided by meter to the 6th. So this has a unit joules meters to the 6th power in SI. And A is related to B. A is basically P over 2, 1.13 times 10 to the minus 10 to the power 6, and that makes 6.68 times 10 to the minus 138 joules meters to the 12th power, as we can see from the potential energy function. Okay, so to summarize, we're talking about the Lennard-Jones potential between two atoms in a diatomic molecule. R is the distance between the atoms. The potential energy varies with R given by this expression. We want to find the force between the two atoms as a function of R. Draw U and F as a function of R. We need to know the equilibrium distance, find if the equilibrium is stable, and then we want to evaluate this potential energy at the equilibrium distance and find the energy needed to separate them to infinite distance, that's dissociation energy. And finally, we apply to carbon monoxide for given A and B values. So the first thing I did was to find the force, I take minus du dr. It's a conservative force. Force is minus du dr. So that gives me the force as a function of R. Then I analyze the behavior of these functions by looking at limit as R goes to 0. I find that the potential energy goes to infinity. Limit as R goes to infinity, I find that it goes to 0. To find the extremum point of this function, I take a derivative with respect to R, set it equal to 0, which means the force is equal to 0, equilibrium point. So I find the equilibrium point R0, and then I evaluate the potential energy function at the equilibrium point to find its value is negative, minus p squared over 4a. So this gives us the plot that we can see here, and by analyzing the behavior of the derivative du dr and multiplying it by -1, I find the force. Force is minus du dr. The derivative is negative here, which means the force is positive. We have a repulsive force for R less than R0. Then we have at R0 a 0 derivative, which means the force should be 0 here, and then the derivative is positive initially. That means we have a negative force, and then eventually the derivative goes to 0, which means the force goes to 0. so at infinite separation. So we see that we have a repulsive region and attractive region between the two atoms. The equilibrium distance is found by setting the force equal to 0, which is what we did in part A. And then by looking at the second derivative of potential energy function at the equilibrium point, I see that this has a curvature that is basically negative curvature. So it has stable equilibrium. So we have a change of slope here. The equilibrium is stable. If I evaluate the potential energy function at R0 and I find the difference between the energy of the potential energy of the system at R equals infinity and R equals equilibrium distance, this is the dissociation energy, B squared over 4A. And then I set the values for R0 and delta U for the carbon monoxide molecule and evaluate A and B from these two results, and basically we find A and B values corresponding to carbon monoxide molecule in this manner.